You know, it's going to be a good day when all I have to do is walk in the room to get a round of applause. So, feeling all right? Even though it was mostly TAs. I'll take it. So last week you all had your lab quiz and interview. I just want to give a heads up on how we go forward from here. So the interview and quiz, they take a while to grade, and we can't even start grading until Friday night. There's a lab Friday night that ends at 10, so we can't even start grading until we have all the results, or else logistics just becomes messy. I want all the grading done before Friday's lecture, and then by Friday's lecture you'll know how you did on those. Each one of them will be pass-fail, and you'll get some feedback on how you did on each of them. The results will be posted to Autolab. Again, by Friday's lecture is the goal. I don't anticipate missing that deadline. By Friday's lecture, you'll see in Autolab next to pale blue dot, there will be two more sections in the LO1, two more assignments in the LO1 submission section. I got my words messed up there. But there'll be two more assignments in that category, which will only be for posting your grades. You won't submit anything there, but it'll be the write and explain portion, or the read and explain portions. So you'll know what you did on those. There will be your score, and then you can click on your score. It'll either be a 1 or a 0, and then that'll give you your feedback. So give us time to grade, be a little patient with us, and we'll get that out to you. By Friday, I want the results by Friday because you need to know if you're going to lab next week. If you got a 1 on both the interview and quiz, you don't have to go to lab next week. You can still go and kick back and hang out with the TAs, ask questions, maybe. If they have time, they'll be busy doing other things, doing the makeups. But if you got both of them, you can take the day off of lab next week. If you missed either one of them, show up to lab. The TAs will have another version of the quiz for you, and they'll be able to do another interview. If you need one or the other or both, show up to lab. It'll be the same exact procedure as last week. You'll take the quiz if you need it, and then you'll do the interview. If you just need the interview, you're going to sit around waiting. You might have to wait for a while, do your interview, and then cut loose. If you just have the quiz, you got the full time to do your quiz, et cetera, et cetera. You get the idea with that. But you have that at least one more opportunity inside lab, and then if you don't pass them both by the second opportunity, then a TA will reach out to you and we'll talk about how to proceed forward. You'll at least get a third opportunity. I like giving you lots of opportunities to prove that you know your stuff in this class. The grading policy seems harsh at first, where it's like you have to do all these things or you fail even if you miss one of them. But I give you plenty of opportunities to pass and show us that you completed each one. And I want to do that here. We have 2 lab periods dedicated to each learning objective, quiz and interview, and then a third being reached out by a TA and scheduling a third attempt. And then at least a 4th attempt with me. Nobody fails the class without talking to me. I want to see everybody firsthand and see if are you actually that clueless? You didn't pass it the 3 times. I want to make that determination myself. I don't want to see somebody get screwed out like maybe 3 times they just happen to get a TA in a bad mood. You know, I don't foresee that happening, but I don't want any % chance of that happening. So I'll have that 4th opportunity to talk to you face to face or over Zoom. And make that determination. And if you clearly don't know your stuff, sorry, that's where your journey ends. But if you do know your stuff, I want to make that determination and give you that last opportunity. So don't stress over these. Study, prepare, best foot forward. But I don't want to see students stressing over it. Your job is to learn the material. It's my job and the TA's job to find out that you know your stuff and give you credit for that. Sup, Dragos? So reminder, I do have the lecture channel. If anybody's wondering why I say Sup, Dragos at the beginning about each one, it's because he says hi in the chat each time. But I do have the lecture channel open on Discord right here. If you have questions, post them there. I don't always have time to check it during lecture, but the TAs are always in there. Usually if I see a student sent something and a TA responded, I usually ignore it during lecture. So TAs, if there's something that you can't answer in there, something that needs my attention, just bring it to my attention, just raise your hand or something. And the old-fashioned raising your hand and asking a question always works as well. Okay, with that, any questions about logistics, course structure, grading, quizzes, interviews, pale blue dot, anything before we get into content or point of sale? If not, we're going to journey into the world of inheritance. Okay, let's journey into the world of inheritance. Yeah, so this week's lab, it'll be, so the same structure that we did with the pale blue dot prep lab, it'll be the same structure as that. The TA will go through the lecture tasks, and then you'll come up with your test cases, and then share those test cases with your fellow students and present your test cases one at a time. And during that time, you should be coding up those test cases, get them in your test suite, and then submit to AutoLab. See what AutoLab says about those tests that you coded up. We had some minor confusions last week. I don't think anything too serious, and I'm clarifying this with my TAs as well. But the TA should be helping you write those test cases and making sure you're leaving that lab with some really solid test cases. If you're listening to the other students present their test cases and you're not sure how to code them up, let the TA know. Let them help you to figure out how that should be coded. This is one case, and I have the waiver in the document itself, but it's worth repeating. There's one case where you can actually kind of share code with each other, at least the specifics of test cases. The TAs can help you go through the code. This is one place where I'm okay with you getting what we would call too much help in other cases, like coding up the lecture task, because I want to make sure everybody has good test cases. So you understand the importance of having good test cases. If you have good test cases before you write your code, it makes writing the code way easier. It's a really huge benefit, and I want to make sure everybody gets to experience that. If you're always writing your test cases after you write your code, you're not going to understand the value of test cases. You're much less likely, anyway, to understand the value of test cases. And the document's posted. It's pretty much the same as the last one, but I give a few Project 2 specific tips and pointers on there. All right, lecture task 3. We're on lecture task 3 of point of sale. Let's talk about it. So for this one, you're going to write 4 new classes. You're going to write a modifier abstract class, and then you're going to write 3 classes, sales, sales tax, and bottle deposit, which extend or inherit that modifier class, and then implement certain functionality. I won't go through every piece of functionality here, but this is what we want to do. So there's 2 keywords that we need to know, 3. Abstract. What's an abstract class? What does it mean to inherit a class or extend a class? I'll use inherit and extends somewhat interchangeably. So let's talk about what inheritance is and extending classes is. I'll pull this up at the end of lecture again, but I want to talk about stack and heap just really quick. So any values that go on the stack directly, I've been calling these primitives, and I'll put it in air quotes usually because they compile down to Java bytecode primitives. That's a little bit misleading. We don't really have any concept of primitives in Scala because everything's an object. Everything is an object. So more specifically, anything that inherits any val is going to go on the stack directly, and anything that inherits any reference is going to go on the heap, and then all of its state variables will go on the heap. So again, we don't know what extends means, but inherit means, but I'll circle back to this. So what does it mean to extend another class? What does inheritance mean? What does this mean? That's what we're building up to. And we're going to take a while building up to it just to make sure that if I dive right into inheritance, I just introduced classes a week ago. I don't think it's going to really hammer it down. So let's back up a little bit, talk about objects and classes, and then dive into inheritance. And let's do it by example. So we're going to do a little bit of world building. We're going to expand the ideas that we had with our player class and build up a little bit of the structure of a simple game, a dodgeball game. So in this game, we want a 2D top-down space where players can navigate. They have some location in this 2-dimensional space, and they have some orientation, which direction they're facing. They have health and strength as part of their state variables. There are dodgeballs in this space that they can interact with and throw at other players, and they have health potions that they can collect and consume to be able to drink. So we might not build this full game, but we're going to build some of the functionality, some of the core features of this thing through this lecture example. So there are 3 different types of object in this game: player, dodgeball, health potion. So let's go through these and define them with a little bit of code. For a player, based on the description, there's a few state variables, some state and some behavior that we can define that a player has to have. So for the state, location, orientation, where are they and which direction are they facing? How much health do they have? What's their max health, which we saw when we defined the player class. We messed with max health and health. And then we're going to add a strength state variable for how hard they can throw a dodgeball for our purposes here. And then 2 methods for the behavior: use a dodgeball and use a health potion. So that's going to look like this. We have our state variables, and we have our methods, which are just going to defer to the dodgeball and potion classes to decide how the behavior is going to go, and we're going to pass it a reference of this player. Dodgeball, we're going to have a location and a velocity. We don't need to know which way a dodgeball is facing. It's not really going to be important to us, but we do want to know which direction it's moving. So we're going to track its velocity instead of its orientation. And we want to know the mass of this dodgeball so we can know how bad it's going to hurt when it hits a player. And then the behavior is going to be use, the method that we saw called in the previous slide. We're going to initialize these values, these state variables, and then we're going to have this method which takes a reference to a player. In the previous slide, we passed a reference to the player that's using that item. So we have a reference to that player that's using this dodgeball, and then we're going to access that player's state variables to decide what the velocity of that ball is going to be. And we're going to use, it's defined in the repo. I didn't put it on the slide, but this physics vector class, which is going to be a vector which can have up to 3 coordinates in x, y, z. So I'm just using that class to be able to store x and y for this 2-dimensional space. So I'm going to create a new velocity, a new physics vector, which will be the new velocity, based on which direction the player is facing and how strong they are. Which, looking at it, yeah, I should probably incorporate mass in there too, but we're just using a simple example here. Kind of do want to build out the whole game though, looking at it. Can you have extra points if you actually build the game? Well, I don't really have points in this class, but you'll get something. You'll get something with no monetary value. I don't know what it is yet. My gratitude, I guess. I'll say it's cool. I'll play it. I'll play the game with you. We could play it during lecture even, if we have time. And then the health potion class, same idea. We have state variables, physics vector, and int for the location and volume. And then when a player uses this, we're going to increase that player's health by the volume of the health potion up to their maximum HP. We don't want them to overflow over the maximum HP. So we're going to have a little bit of math to be able to do that. I'm actually using the min method of the int class that's going to give me the min of these 2 values. Either their current health plus the volume or the max health. Min is going to return the minimum of those 2, and then set that to the player's health. All right, so we have 3 objects in our game. But this game is not very compelling if we build it this way. There's a huge problem with the fact that we used objects, and that's that we can only have 1 of each of these types. We can have 1 player with 1 dodgeball with 1 health potion. Not a very fun game. It's not even multiplayer. Who are you throwing these dodgeballs at? This is not great. It could work. We could build a game like this that works. You can go pick up that one dodgeball and throw it, try to get it to bounce off the wall and hit yourself if you build all that physics. But it's not a fun game. This is why we use classes. This is exactly why we use classes. We want more than one object of a particular type. So instead of declaring these as objects, we're going to declare player, dodgeball, and health potion as classes, which are going to let us create many objects of those types. So we can have a multiplayer game. We can have more than one player object. We have more than one dodgeball object, more than one health potion class, or more than one health potion object. So we use classes to create to define a type and then create many objects of that type, as many objects of that type as we want. Without classes, can't really do that. So let's rewrite these into classes instead of objects. And with classes, we're going to define a constructor for each one of these types. And that constructor is going to be called whenever we create an object of this type. So we want to think these 5 state variables that we have, which of these variables do we want to allow somebody to initialize, or that we want somebody to initialize when they create an object? So looking through these, I think location, orientation, max health, and strength are all values that might change and might want to be initialized to different values when an object is created of type player. So I'm going to put all those in the constructor. This is me saying, hey, when you create a new player object, give me these 4 values. Let me know what you want for these 4 values, because there's no obvious answer for me without hard-coding things, without just saying every player is going to have a max health of 10. Without doing something like that, we can't let them change these things. So I'm going to put these in the constructor and say, whenever you create a player, you tell me what you want the max HP to be, location, which way they're facing, and their strength. There's one value that we don't want them to change, and that's max health. That's health. So the health we don't want them to set. We are going to say every player object that's created in our game is going to start off with max health. They're going to start at full health. It doesn't really make sense to allow people to create players without full health. If they want to do that, they'll have to write a little extra code themselves. We're going to say their health is always initialized to max health. So that we're going to keep out of the constructor and initialize that ourselves. So we have a little bit of logic. Health equals max health, done. Don't make the caller set both the max health and the health. It's just a little redundant, assuming that's the behavior you want. If you want them to be able to create players with different health and max health, but that's a design decision. I'm going to say, put it here, start with max health. And then the behavior stays the same. For dodgeball, I want them to set all of these state variables in the constructor. So if you create a new dodgeball, and I say them, but it's probably you who's going to be instantiating these classes. What do you want to initialize when you create an object of this type? You're going to want to set the location, velocity, and mass. There's an argument to be made that velocity could be initialized outside of the constructor and set to 0, 0, and say you can't have a new dodgeball added to your game that's already moving. Maybe you want to do that, maybe you don't. I'm going to put all 3 of them in the constructor and say whenever I create a new dodgeball object, I'm going to specify these 3 values. I have dodgeballs with different locations, different velocities, and different masses. Again, behavior stays the same. And then finally, health potion, location, volume in the constructor. When we create new objects of this type, we're going to give it both the location and volume. All of its state is going to be defined in the constructor. And now that these are classes, we can create multiple objects using new and have multiple objects of these types in our game. So when we have this dodgeball class, we're going to say new dodgeball, call the constructor, give it all the state that's initialized in the constructor, which is all of the state period for dodgeballs. And we have multiple objects on the heap of that type with different state. These dodgeballs don't share state. They have the same variable names for their state, but with different values. So they have different different values for each of their variables. And technically, it wouldn't fit on the slide, and it's not really the point I'm trying to make right now, but the physics vectors would be references to other objects on the heap as well. So we have two different objects with different state, same state variable names, but different state. And then these two dodgeballs can exist in our game with those different properties through their state variables. All right, so that's mostly all review, I guess, of objects and classes. Any questions up to this point before we really get into inheritance proper? Let me scan for questions on here. Or the references be stored at, like these numbers? These numbers are decided by the JVM. These numbers aren't meaningful to us unless you really know the inner workings of the JVM. You're just going to get some numbers. In practice, looking in the debugger, usually they are sequential, but you'll notice that they'll skip numbers, and it's just details that we as programmers don't need to concern ourselves with, at least at this level. If you do want to get into compilers, I recommend taking compilers with Dr. Alphonse. He teaches an entire class where he's going to go into crazy detail about this stuff. If you're interested, take that class, learn about that stuff. For my purposes, I'm choosing random ass numbers here and then just throwing them on the slide. So, because what I'm concerned with in this class is that you understand this means that that's a reference to an object on the heap. Yeah, exactly. They're arbitrary to us. And those numbers specifically, those numbers this doesn't mean, when you see these in the debugger, that number doesn't mean your dodgeball is stored at memory address 54224. It doesn't mean that that's where your object is stored, but that reference can be used to look up the actual memory address. But the JVM has a few layers of abstraction between the actual memory and how it's represented to us in the debugger and in the JVM with these ats. Those numbers aren't very meaningful to the memory. They're not very meaningful to us, but the JVM can take that number, look up the memory address, find it, then actually find our information. But when we need it, we just say, hey, JVM, here's that number you gave me. Here's my reference. Can you go find my stuff in memory? All right, anything else on this? Or if you're interested right now and you don't want to wait till the compilers class, stop by Dr. Alphonse's office hours. I'm sure he would love to talk about it. In office hours, we love to talk about stuff, just stuff that we're interested in. So most of office hours is helping you debug your homework assignments. If he's in the middle of that and you walk in and say, so the JVM, how's this thing work? Oh, man. He would be excited, just like I'd be excited if somebody comes into my office hours and asks a question like that. Don't hesitate. If you have questions like that, don't hesitate to come to a professor's office hours and ask a really advanced, crazy question that's in their field of expertise. They're going to love it. And we'll probably talk too much. We'll talk until you're sick of hearing us and you'll want to try to leave. But we'll give you all kinds of information. In his field of expertise, he's all about compilers. That's one of his areas that he really knows well. If you want to know about web stuff, I really know web stuff well. Come talk to me. He knows compilers really well. And, Dr. Hertz. Dr. Hertz knows a lot about garbage collection and the JVM specifically, a lot of JVM stuff. But garbage collection, was his focus, if you're interested in that stuff. For what it's worth. We all have our specialties. Mine is not compilers, by the way. I leave I know how to use it, and I leave the abstractions up to the compiler. All right. We could add a potion seller. We could have a player that sells potions. We could do that. So let's talk about inheritance. Let's define this thing and get moving with some new content. So if we look at these two classes, Dodgeball and Health Potion, they have quite a bit of similar functionality. Specifically, they both have a location, and they both have something related to their physical properties, and they both have a use method with the same exact signature. So we have a decent amount of similarity between these two between these two classes. So let's see what we can do with that. So what we want to do is take that common functionality, what we can do is take that common functionality and effectively factor it out into a separate class. And these classes, with these classes, you know, it's not too critical because you would just write both of them. But keep in mind that these classes can have a lot more state and behavior that just doesn't fit on the slide. There could be tons of code in these classes to define exactly how an object is going to behave in our game. So there can be a lot more than just what we have here. I just cut it down for the slide. So let's factor out all of that common functionality, all the common state and behavior, and put it in a separate class. I'm going to call that class Game Object, and then I'm going to have Dodgeball and Health Potion both inherit Game Object. This is where what we call inheritance, when one class is going to inherit from another class, and then Dodgeball and Health Potion will inherit all of the state and behavior of Game Object. So now Health Potion and Dodgeball don't have to define a location state variable. They don't have to have an object mass method, which is a new method we're going to write, or that use player method. They're going to instead inherit it all from the Game Object class. So we're going to remove a lot of our duplicate code. Whenever we have duplicate code in two classes, we could think, well, let's factor that out into a common class and store it there. So what we can do with Game Object is declare it as what's called an abstract class. So an abstract class is a class that's not fully defined. It can have some state and behavior that's completely defined. Here we have location, fully defined in the constructor, but we have two methods, object mass and use, which don't have bodies. These are methods with no bodies. That's crazy. You can't have a method with no body. And it's true, you can't have a method with no body. So what are we doing here? This is what we call abstract methods. And when we have an abstract class with abstract methods, whenever another class inherits this class, they're going to get these methods, but these methods don't have any definitions, so it's up to the inheriting class to actually define the behavior of these methods. So we have an incomplete class, an abstract class. It's like an abstract concept. You can't really get a grasp on it. It's not a real thing. But it can be used to create real things as long as they implement all of the abstract functionality. And then they get this constructor and a guarantee that these methods are implemented. So we have these methods that don't really exist. So when we want to inherit this class, we're going to use the extends keyword. Now with our Dodgeball class, we're going to have the same constructor in this case, and then we're going to put extends right after the constructor parameter list, extends, and then whatever class we want to extend or whatever class we want to inherit. So now we're going to inherit from the Game Object class all of that state and behavior. So we get everything in the Game Object class. Sure, it doesn't look like much right now, but we'll build up to that. And then we have to, what's the next slide? We also have to call the constructor of that class. So when we extend a class, we're calling its constructor right in our constructor line, our definition for this class. So we say class Dodgeball, parameters of Dodgeball, and then extends a call to the Game Object constructor. Game Object takes a physics vector, so we have to give it a physics vector. Now, when we're extending a class like this, when we inherit a class, if we want to reuse a variable name, so I have two variables named location here. If we want, so Dodgeball has this location, and it also inherits this state location. But we still want people to provide a location when they create a Dodgeball. If we want to reuse names, now one thing you can do is just don't reuse names, make things simpler. But if you reuse names, only one of them can be declared using either var or val, or else it'll be a name conflict. You'll have two variables, two state variables with the same name that can both be accessed from outside of the class. So then when somebody accesses it, which one is going to be accessed is a question, is a problem. Here I'm going to take a location. This one can't be accessed from outside the class, effectively private. We'll pass a reference to that, which will be stored in the public location variable. And since both of these variables refer to the same object, we're not going to have any conflicts there. When we say location, whatever one is looked up, it's a reference to the same physics vector. But the point is, that was a long way of saying, you have to call the constructor of the class that you're inheriting. So when you say class sale extends modifier, if you have it's a bad example because modifier doesn't have a constructor, but you would have to call the constructor, any parameters that it takes, you have to call it in that extends. And then any of the methods that were not implemented in the abstract class, you have to implement in the inheriting class, in what we call the concrete class, because this class is a tangible thing that we can create. So here, we're going to implement each one of those, and we're going to use this keyword override to specify that this is something that I've inherited, and whatever I got for this method, I'm going to override that behavior, which in our case is no behavior at all. We're going to override that with this definition. So when a Dodgeball has its object mass method called, we're going to return this dot mass, just the mass of the Dodgeball. And then we're going to override the use method. Oh, that's bugging me. This should be one space over. Fail. All right. The use method with the behavior that we had in the Dodgeball class before, except now we're overriding the use method from GameObject to have this functionality. And same thing with Health Potion. So Health Potion, we have our constructor that we had before. We're going to have people create new Health Potions the same way we did before. We're going to extend the GameObject class, abstract class, give it, call its constructor, and then override the behavior. Here with object mass, we want to do a little bit of work here. We have volume, and we want to use that to to compute the mass. I'm just going to multiply by 7. We're going to say that per volume of Health Potion, we have 7 mass, whatever the units our mass are, whatever our units for mass are. And then we're going to return that, whatever the volume is times 7. So we have two different definitions of the object mass method, and which one is called is going to depend on the type of the object, whether it's a Health Potion or a Dodgeball. They're both game objects, and game objects are going to have an object mass method, but which definition depends on the actual type, Dodgeball or Health Potion. They have different definitions for the same method name. And same with use. We're going to take that use method from the Health Potion class and add that to our overridden use method in this new class. No, so you can't overload methods in Scala, right? Yeah. Oh, I had to second guess myself there. All right, I use too many different languages these days. I'm pretty sure you can't overload methods in Scala. So you can't have two methods with the same name with different parameter lists inside the same object. I want to say that's true. I'll hedge my bets on that and say maybe that's true. It's something I haven't done ever in Scala. I'm pretty sure I don't do it because you can't. But it's worth a try. Somebody can try coding that. Dragos, if you want that answered. Try coding it, you can let me know. Right, but you can have default values. And that really eliminates the need for that. You can have default values on your parameters. But that's a little off track for today's lecture. I already mentioned all that. All right, but why? Why would we ever want to do this? So in this example, I would argue that we just did more work. We created more work for ourselves to get the same functionality that we had before. So why do we want to do something like this? Well, this is where if these classes were a lot larger, we would see the benefit of this a lot more. And if we had more object types, we would see this a lot more. So first, what if we want to add functionality to both our health potions and our dodgeballs in this game? We want to add the same behavior to both, but we want to add it to both of them without duplicating code. We don't want to go into each class and duplicate the code. As a general rule of thumb, if you have duplicate code anywhere in a software project, there's a better way to write that code, is just a general rule of thumb. So let's add some behavior to both those classes, and to add that to both the classes, we're just going to add it to the game object class and let both of those classes inherit that behavior through inheritance. So let's add this close to player method, which is just going to return a Boolean. Take a player and return a Boolean. Are you close, whatever close means, however we're going to define close, to this player. And we're going to define if they're within 0.5 units from the player in this 2D space. So we're going to compute the distance between the player and this object, this game object. And if it's less than 0.5, return true, else false. We write this method one time only, and now health potions and dodgeballs both have this method. We wrote it once, we get to use it in two places, much more effective and efficient, especially if we have a lot of math. Maybe we have another equation, maybe we're doing greater circle distance, and we don't want to write greater circle distance, test it, then copy, paste into another method. Things start getting bad after a while. You keep cut and pasting. And what if you cut and paste multiple times, and then you want to update that functionality? Maybe close to player, maybe I actually want this to be 1.0 instead of 0.5. If you have it in separate classes, you have to go to that class, each one of those classes, and make that change. And make sure that you do it consistently, and things like that, just ask for bugs. Well, I changed it there in Health Potion, but I didn't change it here in Dodgeball. Now everything's broken, and I'm not detecting collisions correctly. Players, this specific thing would probably be when a player's walking and there's a dodgeball there, if they can pick up that item. If they're close to player, pick up that item. Would probably be my functionality here. So I add it into the abstract class or the base class. There's a lot of vocab here. I'll try to be consistent and just use one set of terms. But I want to say them all at least once so you hear them. But we add it once to the base class, the abstract class, and all of the inheriting classes get that behavior, all subtypes. Right now we only have two, but you can think, if we're designing this game, you can think up a lot more items that we might want to have. Maybe we want to change this into a hand-to-hand combat game. Maybe we want swords. Maybe we want sticks that you can swing. Maybe we want bow and arrows. Maybe we want gold that you can pick up. There can be countless item types that you want to add to this game, and every time you add a new item type, you don't want to be cut and pasting some close to player method every single time. Or any other behavior, collision detection, you don't want to be able to be writing collision detection code in every single object. When you add a new object to your game, you want to only be thinking about the functionality, the state and behavior that's very specific to that object type. So if I'm adding a new bow and arrow, I might want to add my quantity of arrows that I have, the damage it's going to do, the velocity it fires an arrow, things related to a bow and arrow. But I don't want to be messing with anything else. Anything that's not specific to that item, I don't want to have to care about when I write that item. Put it all in an abstract class and let that abstract class give that functionality to that new class. It keeps things much more organized, and it's a lot cleaner to be able to, like adding a new item to your game, an item type, should be no big deal at all. You just extend game object and give it the specific properties you want. So say if I have 100 types and I want to change this close to player behavior, I change it one time, and all 100 item types just got their behavior updated. There's always more, but there's nothing in here that relates. So I mentioned collision detection. Maybe we want collision detection. Maybe we want gravity to affect these objects. Maybe we want anything related to physics to be applied to this. Well, no big deal. So assuming it used to be a homework, I got rid of the homework because, well, there were complaints about it being too hard. But there was a homework where you would build a physics engine and do collision detection and things like that and add all that. And the whole physics engine worked off of a physics object. It didn't care what objects it was computing on. It would just take a physics object and do its computation on that. Take a bunch of physics objects and do collision detection. If it had a velocity, move it forward by that velocity by some delta time. Detect collisions. I said that already, like multiple times, right? So anyway, if we want these objects to work with our physics engine, and we don't want to rewrite physics for every single game we write and for every single object type in that game, guess what? We go to our game object class, and we extend physics object. Now, all of our objects, our health potions, our dodgeballs, and anything else we can think of, is now a physics object. And we can use our physics engine and apply that to every object of our game. Now, when we wrote our dodgeball class, we weren't thinking about how is this thing going to move through our two-dimensional space, or three-dimensional if we incorporate gravity. But once we, in some other class, extend physics object, now that dodgeball can have physics applied to it. The physics engine can take that dodgeball and figure out how to move it through this space without the dodgeball class ever having to care about that. It just needs a location. Once a physics object, which will have a constructor which takes the location, forward that location, and that's it. And then, assuming you have the whole physics engine written, of course, then a dodgeball and health potions can have physics applied to them. So this brings us to our inheritance structure, our inheritance tree, where an arrow pointing to a class means that this class extends that class. So dodgeball extends game object, which extends physics object. So that's all I wanted to say about that one. So we can picture our inheritance structures graphically. So a health potion defines the volume state variable, but also inherits all of this state and behavior, and inherits this state, and anything physics object extends, it'll also inherit that. So we have a whole inheritance tree, and you can follow the chain up to any inherited classes to be able to get all of the state and behavior of health potion. So you start with physics object, game object, health potion, collect all of the state and behavior, and health potion gets all of that state and behavior. Which brings us back to that picture earlier in the lecture. So this is the inheritance structure of Scala. So Scala starts with the any class. This is the base class that absolutely everything inherits. Everything has the state and behavior of the any class. If you're coming from Java, this is like the object class. Everything extends object. Everything extends any in Scala. There are two splits here. Any can be extended by any val, and that's all of our classes here. that go on the stack. So double extends any val, which extends any. So double has all of the functionality of any val in any. The any val functionality, part of its functionality says, I go on the stack. Any ref also extends any, and this is the same as Java lang object, as you can see. So if you're used to Java and everything extends object, well, not everything extends objects because the primitives don't. So Scala adds this extra layer to specify that, no, we don't have primitives. Those are also objects defined by classes. So any ref, everything else extends any ref. Any ref, for reference, these are going to be stored on the heap, and the references, their references are stored on the stack. Only references are passed from these. List, string, map, everything else, everything that's not one of these any vals is going to go on the heap, including your classes. Every class that you write is going to go there as well. So inside this box right here is everything, every class that we create in your class. So our inheritance tree actually looks a little bit bigger. We're going to have health potion, which extends game object, which extends physics object. With physics object, which you can see in the repo, I don't have it on the slides here, doesn't extend anything. I think I might have had it extend something. No, I don't think I did. But it doesn't extend anything. Any class you write that doesn't extend anything implicitly extends any ref. So if you don't say extends, if you don't use extends at all, implicitly you have extends any ref. So our physics object extends any ref, which extends any. So our health potion has the functionality, the state and behavior of all of these classes, all 5 of these classes baked inside of it. This brings us back to our lecture task. All right, any questions? Anybody got anything? Anything in chat? I think those have all been answered, right? All right. Have a great day. I'll see everybody Wednesday.